To be able to evaluate an average velocity, you first have to choose a time interval, a Ti and a Tf. For this trajectory, the displacement for the whole trip is shown in red. If you keep the same initial time value but choose a much closer Tf to Ti, the displacement vector could look like this. The smaller the difference between Ti and Tf, the more parallel the displacement will be to the trajectory. Since the displacement is in the same direction as the average velocity becomes nearly parallel to the trajectory. With an infinitely small delta t, the Ti is almost the same as Tf, and the average velocity becomes an instantaneous velocity, no longer associated to a time interval, but linked to one time only. With a small delta t, the trajectory within that small time interval is nearly a straight line, and the average velocity describes how fast the object is moving for the entire interval, and its direction is parallel to the trajectory. Here are some examples of velocity vectors at various points along the trajectory. Let us apply the same procedure to the average speed. As the delta t becomes small, the trajectory becomes a straight line, and the distance traveled becomes the same as the magnitude of the displacement. In a loose mathematical form, this statement can be written like this. Notice that the subscript avg has been removed. The process of letting delta t become very small transforms the quantity that is average to an instantaneous quantity. The variable v arrow without the avg is the instantaneous velocity, which we will call the velocity from now on. The magnitude of the velocity leads to an expression that is the same as the one for the speed. The magnitude of the velocity is called the speed. Let us look at a one-dimensional case. Here is a component of position versus time graph. For the interval Ti to Tf, you can draw a line from the point Ti di to the point Tf df. We know already that the slope of this line is the x component of the average velocity. If you bring the Tf close to the Ti, the line segment joining Ti di to Tf df becomes nearly parallel to the red curve when Tf is very close to Ti. This green line is called the tangent to the curve, and it crosses the curve at Ti di, and its slope is the same as the slope of the line segment joining Ti di to Tf df, when the difference between them is infinitely small. The slope of the tangent line is equal to the x component of the velocity. This slope of the tangent line can vary from each point of the curve, so the velocity is a function of time. Let us look at a special case for the relationship between dx and time, a linear relationship. Evaluating the slope of the line gives us the value of the x component of the average velocity. Since we are working with a line, any time interval will give the same result. This result will be the same if we let delta t become infinitely small, so the x component of the velocity is also equal to the slope of the line for all values of time. In summary, for this special case, the x component of the average velocity and of the velocity are constant and equal to the slope of the line. For example, if dx equals 100 km per hour times t plus 300 kilometers, we have the equation of a line, and the number in front of t is the slope of the line. So the x component of the velocity equals 100 km per hour for all values of time. We should be able to get the x component of the velocity by evaluating the slope of the tangent to the curve of the x component of position versus time graph at each point of the curve. As an example, we will use this x component of position versus time graph and create a rough graph of the Vx versus t from the dx versus time graph. The sharp point of the graph of dx versus t at t equal t1 is unrealistic because a proper tangent to the curve cannot be assigned there. But we will ignore this problem for the time being by not evaluating the x component of the velocity at that point. The relationship between dx and time for the interval from 0 to t1 is a line with a positive slope. So the x component of the velocity is a positive constant. Since no scales have been given on the axes, we will not be able to evaluate a number for this velocity, so we will just show this insight like this. Between t1 and t2, the function representing dx versus t is also a line, but with a negative slope. Representing the velocity for that time interval also leads to a constant value, but a negative value. The dx versus t function shows a transition between a line to a curve at t2. The tangent to the curve at t2 could look like this blue line with a negative slope. But the red tangent to the curve at t3 would be horizontal, which means that it has a slope of 0. At t3, the x component of the velocity is 0. There is no hint that the relationship between Vx and time is linear, but we will use it here for the sake of simplicity. After t3, the slope of the tangent to the curve keeps increasing until a high positive value at t4, as can be shown with this green tangent to the curve at t4. We will just continue using the simple linear relationship with positive values for Vx for the interval between t3 and t4. When the x component of the velocity is constant for a certain time interval, it means that the relationship between dx and time is linear, and the slope of that line equals the constant Vx value, as well as any evaluation of the x component of the average velocity. In other words, for this special case, the x component of the velocity equals the x component of the average velocity, which is equal to the x component of the displacement divided by the duration of the time interval. Let us rewrite this equation slightly differently and choose a time interval on the graph. We can draw on this graph an orange rectangle bounded by the horizontal t-axis, the vertical lines at ti and at ti plus delta t, and the Vx curve, which here is in an horizontal line. This is called an area underneath the curve for the time interval ti to tf. The geometry is such that if the length of the rectangle is Vx and the width of the rectangle is delta t, then the area of the rectangle, which is the length times the width, is the x component of the displacement during that time interval. This is a geometric interpretation of the equation delta dx equals Vx times delta t, even though our length and width are not in meters, and the area is not in meters square. On top of that, Vx could be negative, which leads to a negative area corresponding to a negative x component of displacement. How can this funny application of geometry be useful? Let us look at a more general situation where the x component of velocity varies with time. Could the area bounded by the t-axis and the vertical lines at ti and at ti plus delta t and the Vx versus time curve be interpreted as the displacement over the time interval from ti to tf? Yes, it can. We could split this area into narrow rectangles with length equal to a fairly constant Vx if the width is infinitely small. Each of the tiny rectangles represent displacements over adjacent time intervals that can be added up to get the total displacement for the interval from ti to tf. This mathematical technique is called integration and is beyond the scope of this course. I only mention it here to give you a hint of how the area underneath the curve of the x component of the velocity versus time can lead, in general, to the x component of the displacement. However, we will restrict ourselves to the most basic geometrical shapes of rectangles and triangles. The case where the x component of velocity has a linear relationship with time will have a special place in the next lectures. A car speeding up at a constant rate would be an example of such a situation. As discussed before, the area underneath the curve is the x component of the displacement of the object for the interval from Ti to Tf. The geometrical shape is a rectangle underneath a triangle. Using these shapes, we can write that the area underneath the curve is the x component of the displacement, which can be evaluated by adding the area of the rectangle to the area of the triangle above it. Rewriting this equation by grouping the terms with Vix together leads to this equation. Recalling the definition of the x component of the average velocity makes the delta dx equal to this. The comparison between the two last segments of this equation shows that for the special case, when the Vx versus time is a line, the x component of the average velocity can be evaluated from the x component of the initial and final velocities, and that the x component of the average velocity is in the middle between the initial and the final values. Since the relationship is linear, the instantaneous velocity with the same value as the average velocity occurs at a time in the middle of the time interval, which is at Ti plus half of delta t. This result is useful because a measurement of the average velocity can be considered to be an evaluation of an instantaneous velocity at the time in the middle of the interval, if it is assumed that the Vx versus t is a line during that interval. The last item in this lecture is a numerical example where the displacement of an object is evaluated from a x component of velocity versus time graph. Let us start by giving variable names to the numerical information from the graph. We have the x component of the initial velocity and of the final velocity, and some important time values like the initial time and the final time. Special features in the graph occur at time t1 and t2. Next, we evaluate the area underneath the curve for the interval from ti to t1, to which we add the area underneath the curve for the interval from t1 to t2. And finally, we add the area for the interval from t2 to tf. Substituting the numerical values for the givens leads to this, and to the numerical value for the x component of the displacement. The question is about the displacement, so the final answer is 12 centimeters left, which means that at the end of this trip, the object is 12 centimeters to the left of where it started. This ends our lecture about the velocity. Our next quantity to consider is how the velocity varies with time. This will be the subject of the next installment.